Hello, my name is Armando Pinales, and I will be discussing an autonomous embedded system vehicle design on environmental, mapping, and human detection data acquisition for firefighting situations. I'll begin by introducing the topic, and then I'll discuss the hardware architecture, followed by the software architecture. I'll discuss our initial results, our conclusions, and future work. When firefighters are faced with a burning building, they face a variety of hazards, such as extreme temperatures, low visibility, poor air quality, a foreign building layout, and the unknown location of individuals. All of these challenges make for very time-consuming rescue operations, and this places not only first responders but civilians at a greater risk of injury or death. The goal of this research is to provide a system for firefighters that provides them with the important information and data that they need in order to perform faster and safer rescue operations. So we propose the Autonomous Embedded System Vehicle, or AESV. The AESV prototype is currently designed to autonomously scout a floor when deployed into a building and collect environmental data using its sensors. This collected sensor data is then transferred back to a base station located at the fire truck where it's further processed. And this further processed information will provide firefighters with the things that they need in order to perform faster and safer rescue operations. So now we'll discuss the hardware. The AESV is currently composed of a temperature sensor, a gas sensor for detecting nitrogen dioxide and carbon monoxide, a motion sensor, GPS, an infrared camera, LiDAR, and an XB module. So the overall operation of the system currently is the itsy bitsy microcontroller, which is acting as a slave, will receive sensor data from the temperature, motion, and gas sensors. The teensy, the master microcontroller, will receive GPS, LiDAR, and video stream information as inputs. The teensy and the itsy bitsy microcontrollers both communicate data over a serial interface. I also need to mention that the itsy bitsy is responsible for controlling the motors of the AESV vehicle. An XB radio module is connected to the teensy, which allows us to transmit the collected sensor data wirelessly to a base station for further processing. The current software architecture begins with the microcontrollers booting up and polling the status of their sensors and communication channels. If the sensors are not working properly or there's some kind of error, the AESV will not boot into its normal main program and will terminate. If the sensor and communication channels are working properly, then we begin by updating our navigation and obstacle avoidance systems. We then begin collecting data from all of our sensors. Once the data has been collected, it's transmitted to the base station wirelessly through the XBs using the Zigbee protocol. If the data is transmitted successfully, we return and update the navigation obstacle avoidance system. If it's not received successfully, we try again and retransmit the data to the base station. And we'll know if data was transmitted successfully because upon transmitting the data, the AESV expects a response packet from the base station indicating whether the frame was received properly or not. So our initial results indicate that we've successfully integrated the carbon monoxide, the GPS, and the XB module. Here you can see that we've tested the temperature module by placing it near an open flame and heating it up to approximately 220 degrees Celsius. For the carbon monoxide sensor, we exposed it to a smoke created by a candle suffocated under a beaker. And here the data that we're seeing is the carbon monoxide concentration in parts per million. We've also received GPS coordinates, and they're being refreshed every 10 seconds. We also receive things like time, the date, the fix, location, speed, angle, altitude, and the number of satellites that we are receiving information from. We've also established the communication between the AESV prototype and the laptop that is serving as our base station. So we've been able to successfully transfer a temporary payload from the AESV to the base station. In this case, we've transferred the integer values 10, 11, 12, and 13, and they appear as A, B, C, and D in hexadecimal. Again, these values currently serve as placeholders. In our future work, these will be replaced with sensor values such as the temperature, gas, and GPS values. This is the current breadboard implementation of our AESV unit. So on the top left, labeled A, is the Teensy microcontroller. B is the XB module. C is our carbon monoxide gas sensor. D is the GPS unit. E is our itsy bitsy microcontroller. And F is our temperature sensor. So in conclusion, the AESV prototype is designed to gather environmental data and transmit that to a base station located outside in the fire truck. The result of this is that we provide firefighters with important information that they need in order to perform faster and safer rescue operations. We've successfully integrated at this stage the temperature, carbon monoxide gas, and GPS sensors. We've also established the transmission of placeholder data between the main controller and the computer that's currently serving as our base station. In our future work, we'll begin integrating the LiDAR and infrared camera modules. After we've fully integrated all of the sensors into the prototype, we'll begin the development of a program that runs on the base station, which will process the obtained sensor data from the ASV, and we'll be able to develop a 2D map based on the LiDAR information. The program will also display the location of the most extreme temperatures in the building and the locations where the harmful gases are present. Another thing to consider is the integrity of the sensors on the ASV unit. You never know when a sensor is going to go bad or something malfunctions. So in our future work, we'll also consider a system for detecting when faulty sensors or a sensor malfunctions. We're considering doing an integrity check where we have redundancy sensors, which we can compare the two values of the sensors to see if they're within a certain range of each other, a tolerance range of each other, and if one is extremely different than the other, we'll know that something is not working properly. And the main idea here is that one AESV unit will not be enough to cover a large building. So in the future work, it will not just be a single AESV unit, but a network of AESV units, all communicating with each other, all scouting the floor at the same time, and all collecting data, environmental data, and transmitting that, all of it, back to the base station for it to be processed. The motion, GPS, and GPS data from the AESV will be used for path planning and navigation. The base station will be designed to help in commanding the AESV units as they survey in parallel. We'll also transmit the infrared video information as a stream of data from the AESV to the base station. We're going to utilize the infrared information with image recognition techniques to allow the base station to recognize individuals in the building. That way we can place a location marker on our 2D generated map, and firefighters will know exactly where to go and plan optimal routes through the building and maximize their time and efficiency. Thank you.